Good afternoon, Professor.
Good afternoon, Savannah, and
Good.
good afternoon, Caroline. And I saw that it's perfect. We know the semester is ending because I finally did see the green square on Savannah's. And okay, and we're gonna be fast. Good afternoon, Caitlin. And I saw you, believe me, I saw you right away. Good afternoon, Kevin. Good afternoon, Amanda. Good afternoon, Irini. Good afternoon, Stephen. Good afternoon, Rashman. Good afternoon, Erica. Good afternoon, Amy. Good afternoon, Sumaya. Awesome, awesome. And okay, we are going to. Okay, this is the second to last class. Good afternoon, Jose. Okay. Okay, I have to be careful about time management in the next two classes. Let me get some okay. This is that point in the year where we have to be very careful about balancing academic considerations and intellectual considerations. This is the time of the year where I totally understand, believe me, understand that you are mostly concerned with academics, meaning the closer we get to the end, the more concerned I believe that most of you are about your grades, about what has been happening with your grades or what will happen with your grades. I totally respect that. I get that. It tends to be the case that at this point in the year, I'm more confident about your grades than you are. And that, of course, that's partly because with some of you, you're still waiting on very important grading information. And I totally get that. And the grading information is continuing to come back to all of you slower than it should, but it's continuing to come back. Many of you may have noticed that even if you still haven't gotten your exam yet, a lot of other things have come back. A lot of participation points that you've submitted for, hopefully you're seeing land in your box. It's my way of saying, believe me, I know that you need to know about your grades, and I'm getting all the information to you as best as I can. It will all come out in the wash at the end. Let me again reinforce to you I hope that you trust that if you've been an engaged member of this class, if you've been participating, if you've been turning in the homework, if you've been paying attention, I think your grade is going to work out probably better than you think. But if you have any concern at all, like you're still waiting on information, or you got the information and you don't know what it means, or anything like that, I encourage you to reach out to me personally between now and the end, whether by text or by email. Many of you have been doing that. And I can address things one-on-one. I promise. I can even accelerate certain things if I address things one-on-one with you. I promise you again also that if there's a major concern with your grade, like if I have reason to believe that you're heading toward an F or a D or a C minus, I probably would have reached out to you by now, or I will reach out. And again, let me remind you that if I hit some major surprise, if I hit a major surprise right at a very final moment where I really believe that something surprises me, and I don't want you to be surprised on CUNY first. In the worst case scenarios, on the very last night before the grades are due, and I know I've said this before to many of you, I'm just going to say it one more time now to make sure. On the very worst case scenario, if it's the night before grades are due and suddenly I have reason to believe that you're going to get a D or an F, and I don't believe you know that yet, or I don't believe we've discussed it, or I don't believe that you've had time to prepare for such a shock, then in that scenario, you will see an incomplete on your transcript on CUNY first. And that means reach out to me and we will see what's going on and see what we can work out. Okay. You will not suddenly be shocked with a devastating, irreparable failure in this class that you didn't have time to prepare for. This is all a long way of saying that, again, I hope for the next 2 days, even if you're still receiving information from me, I hope that you could to some extent trust that if you've been doing your job, it will be noticed and recognized and worked out. Sorry, there's more reasons I'm saying that. I'm also saying to all of you, your big job was the midterm, whether you've gotten your information on that back or not. The big hump of this course was the midterm. There will be a final in this course. Hopefully you saw the information on Google Classroom. Like, there will be a final posted no later than 8 p.m. a week from this Thursday, a week from tomorrow. Okay, it's in Google Classroom, again, if you haven't seen it, but the final will be posted no later than 8 p.m. Thursday of next week. It'll be due back before midnight on Monday of the following week. So you have like 4 days to do it. It will be a lot shorter than the midterm. The next 2 days of class will be oriented towards really helping you prepare for it, but it'll be shorter than the midterm. And again, like hopefully you saw in Google Classroom, it's intellectually, it exists so that we can put together all this material and you can see why you've been studying this particular physics for 2 semesters. That's intellectually why the final exists. Academically, it's so that those of you who did not do so well on the midterm or think you did not do so well or are worried that you did not do so well, it'll give you an opportunity to do better. That is, let me repeat again, it's now in writing. Whichever of those 2 exams you end up doing better on will count significantly higher in your average. So if you did get somewhere in the 80s or higher in the midterm, or even in the 70s in the midterm, that is a very good grade. You should be happy, you should be satisfied, and you should not get too stressed out over the final. It won't ruin what you've been doing so far. If it turns out you got in the 60s or something on the midterm, that still doesn't mean you're failing or anything like that. But you can use the final as an opportunity to correct that, and it'll count more. Okay. And I don't want to spend again the next 2 days talking about this again. I'm just trying to say to all of you that I know, I'm sure you're concerned, many of you. I'm sure you're still waiting on information, many of you. I'm getting it to you as quickly as I can. But please trust that I know that, and that if there's really a problem, I will either reach out to you or you'll reach out to me and we'll figure it out. I'm saying all that because once I get rolling in a few minutes, what I really want to, I'll be sort of rushing, but I want you to see the punchline of the physics story that has been unfolding for 2 semesters. I want you to see why you've been doing all this work that you've been doing. I don't want this last final exam to be a huge new academic stress for you. I want you to sort of now be able to sit back for the next 2 days and try to absorb this material, not solve a million problems on it, but just try to see how the material comes together. So again, from here on in, whatever academic concerns you have, I totally get it, but please reach out to me personally so that I can just try to put this material together for everybody while in the background, I'm trying to get back all your grading information or grades. Wait, there's a reason I'm saying all this. So the next 2 days, I'm going to be saying physics concepts that are the final physics concepts that ultimately fit everything together in my judgment. Wait, there was one other reason I'm saying this. Hold on. Okay, yeah. So I will ask once I get rolling with the physics, once I see if there's any, there's stuff in the chat. Hang on a second. Let me see what's in the chat. Very good question. Okay. So good afternoon, direct chat person. There's a direct chat question. Very good question about, okay, since I'm still getting back stuff to you, someone's asking like about the last day, whether you could still submit homework or not. The last day to submit homework, any old homeworks, which let me back up. You can still submit old things to me. You can submit revisions of old things if you want better grades. You could submit homeworks that you never did. You could submit game portal stuff. In fact, quick comment on that. But all of that you can submit until the last day of classes. So really, that's all up to up through the 16th. Like next, I'll put that in Google Classroom as well. But any old things that you're turning in, you certainly still can. But I can't really take them during the final week because I'll be too concerned about grading the final. So up until the 16th, a week from yesterday, please give me any old homeworks you want to give me, and they will count. And please tell me if the person who asked in direct chat, please tell me in direct chat if my answer is clear. The other thing about homework, so is the one thing I don't want to take a lot of, please don't turn in old game turns, like the daily 5-point reflections. That's not worth, okay, great. Thank you, direct chat person. Okay, great. That's not worth turning into me at this point, the old daily check-ins, like especially not a pile of them, but anything else you can. Also notice, you might be noticing as you're getting things back, if you've done 1 or 2 revisions on any particular homework, even if things still aren't perfect or something like that on an old homework, if you did it and then you did revisions and you were improving your score, if you were on that trajectory where you were improving your score and really working on it, then at this point, it's like amnesty. If you've done a revision or 2 on homework and I see that fact, then you will get the maximum points on that homework at this point, just for having tried that hard and seen it through. Okay, even if there are still imperfections, you might notice that some numbers are just increasing on your end without any increased comments. That's because if I see that something was there for a while and you did a revision or 2, then you're getting the maximum points for it. Okay, things like, so I'm still returning all the points to you, including some of you, your midterms. You can still keep turning in old homeworks to me, except for the game turns. And you can do that until the 16th. Last thing also, another thing is if you're concerned about your grade, please remember, like with the style of my grading, with the system, it's the same system for everybody. It's not meant to treat any one person any different from another. But what it is meant to do is treat all of you, is evaluate all of you sort of at your best, as opposed to your worst or as opposed to your middle. So please remember that, like, for example, with the exams, and, partly because I feel like you deserve a big benefit of the doubt because of my slowness with the exams, but also for other reasons, I'm again saying that the one you do better on will weight more heavily for you in your average. That's the same rule for everybody, but it will treat different individuals according to their particular strengths. That's the philosophy in general. So that another way, if you're concerned about your grade or something like that, please remember there's a game portal. There is one particular game portal called Your Best. In that, and I think I've explained this once before, but just to remind you again, because we're getting to that point in the year, or we're at that point in the year, in the game portal called Your Best, you could put anything you want in there, any old assignment that you did really well on that already got graded, or an assignment that you think you're doing really well on, but it didn't get a grade, or if you did get your midterm back and you rocked it, you put your midterm in there, or class notes that you take that I've never seen that you're really proud of, the way you take class notes during Zoom class or whatever. Basically any document that you're the most proud of, any document that you think really represents you at your best in this class, just put it in the portal called Your Best. That is a signal to me. That's a reminder to me of who you are at your best. And it's also a gesture of self-awareness. It shows me that you know the difference between your high quality work and your lower quality work. Put that in the portal called Your Best. You'll get automatic points just for doing that. But also that will help me when it comes to the end. If you're right on the borderline between 2 grades or something like that, that will definitely help me help you push yourself over the edge. The goal here is for each one of you to give me something quality to work with so that can help translate and input into the best possible grade that you can get. Okay, the idea is for you to be judged on your best, not on your middle. I can't say it any really better than that. And for me to give you the best benefit of the doubt I can, and especially because I'm asking you to do the same thing as you indulge my slowness with grading certain documents. Okay. Any other larger questions on that topic? So again, just to clarify, so the next 2 days, once I get rolling now that I've said this, I'm just going to be sort of blasting through physics material, and you should take notes and all that. But please bear in mind that the physics that I'm trying to put together for the next 2 days, it's what the final exam will ask you to understand it, but not in the traditional way. You won't have to solve a million problems on what I'm talking about or anything like that. Don't worry about how can I solve 85 new exercises on these applications. Try to get the big picture of what I'm saying over the next 2 days. That's the goal. So try as best as you can to trust that you've done your hard work at this point. You've done your hard work for 2 semesters. You took the midterm. The ball's in my court to take your input and turn it into the best possible grading outcome. So your job for the next 2 days is to slightly try to relax and absorb the material for the material's sake. Like, try to get what the point of all of this was so that all your efforts actually can materialize both into a good grade, but also into your appreciation of the science that you signed up for with these 2 courses. That's the, so I'm saying all this to get this all out of the way, because once I start rolling, I may talk fast and it may be a lot of intense ideas. Hopefully you'll bear with me and you'll worry about the ideas, not about how well your grades will reflect them. Having said that, first of all, are there any questions on what I just said or what's going on for like what the plan is for the next 2 weeks or week and a half? Is it clear? Any questions? Okay. Can I just get you to raise your electronic hand if you basically feel like you understand? Okay, cool. If you basically get what's about to happen for the next 2 days. Okay. Awesome. 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 Okay, great. Thank you. And I will be in my office next Tuesday again from like 11 to 1 as usual. And I hope we all stay in touch too. I mean, I know I'm going to see you again on Monday electronically, but I hope we all stay in touch. And I hope you seek me out to help support you in your future ambitions and all that stuff. All right. So we're going to turn to physics now. Let me turn on the board. Thank you for raising your hand. We're going to turn on the board, go back to the physics of field lines. Okay. And again, definitely reach to me personally if there's any. Oh, sorry. There's one other thing. It's so awkward. I always almost forget about this, and it's so awkward, or I make it so awkward. I do need to take 10 minutes. That's the other reason I'm rushing. We need to take a few minutes, please, to do the course evaluations or the teacher the faculty evaluation, student evaluations of faculty. Again, I always do find this slightly awkward, but I want to give you an opportunity to have your input as to the course and so forth. So in the chat, I'm reminding you of the link. Some of you may have already done this already. You might have noticed that the link was put in the stream. If you've done it, I really appreciate it. That is great. Thank you so much. But I'm going to ask you right now. Did I do it? Did I just type it in? Sorry. Hold on. But I'm going to ask you to do it right now, the class evaluations. And indeed, you have me for lecture and recitation. It's all the same course. One is Monday, the other is Wednesday. It's all the same. But if I can ask you to fill out a document for each one of those, you can fill out the exact same information if you want, or if you feel that Mondays and Wednesdays are different, somehow you can make that distinction. So I'm going to pause for a second for a few minutes. I'm going to ask you to fill out these evaluations that are at that link that I just posted. If you've already done it, get a cup of coffee for a couple of minutes, and I thank you. And be honest. Oh, and please understand, I know you know this, but they are totally anonymous. I assure you of that. I assure you, I have no idea what you say. I have no idea who does what. I have no idea which one of you did them or not. If you don't feel like filling one out, that is totally your right too. I just really want to give you the opportunity right now to do it. And honestly, they really, I don't know what you say as individuals, but believe me, they really are looked at by all of us. We do actually take them far more seriously than you might realize. It is your opportunity to affect, if not only your own academic future faculty, but it will affect the students that come after you. They actually are taken quite seriously for what it's worth, which is why they make me nervous. So I will shut up. I will ask for you to go to the link and do this. And once you're done filling out one for each of the sections for sure, and recitation. Then please put up your electronic hand once you're done, or just once you're ready to move on, if you're not doing it. And I will shut up. Great. Thank you, guys. Okay. Still going to give, there's no, I totally appreciate it. I see the hands. There's no rush on this. I mean, I'll take your time. If you are raising your hands, thank you very much, and keep your hands up, please. If you're still working on it, please do keep working on it. We'll take a few more minutes, but just when you're done, do please put up your hand. Thank you. And I'm going back and forth. I'm trying not to. Yeah. So, if there are few people still working, that's fine. I'm going to gently start, if that's all right, because I'm not, because some people might be actually have stepped out of the room. I think, yeah, I think you can put your hands down. Thank you. I'm gonna, if anybody, okay, cool. Okay, thanks. I wasn't sure. Okay. Yeah, I don't want to rush anybody. And if anybody wants to direct chat me that they want more time, I will totally honor that. I'm just not sure if everybody's actually literally in the room at the moment. So, but thank you. So yeah, I'm gonna pull up my board again. If you're still working, and then definitely don't rush it. I mean, just send me a direct chat that you'd like a little bit more time, and that's fine. But okay, other than that, I'm gonna pull up my board. Okay, and if you are done, you can put your hand down if you're done. Thank you. Awesome. So hold on, I'm just gonna check in here. Okay, I think, all right. I'm thinking that's everything it's accounted for. Okay. All right. So again, let me try to remind you where we are right now, what the concept is going on here. The concept, again, is we're talking about field and field lines. And please remember, again, I can't emphasize enough that the whole idea, also I'm going to switch this. Okay, the whole idea is field lines over here in space indicate precisely and numerically the location, the magnitude, and the distribution of charge or mass, but we're talking about charge, of charge over here in space. Field lines are the information, the very specific numerical and directional information describing some bunch of charge that's over here at another location in space. So the field is the non-thingy thing that constitutes the information in one point in space of thingy things, stuff, particles, matter, objects, material entities that are occupying some other point in space. The field is the way in which all and any different points in space are physically aware of what's going on at every other point in space. Like that's the concept of fields, right? Fields are the unthingy information mediums by virtue of which portions of space over here know what is occupying space over here. That's what fields are in general, okay? And field lines do that. And Gauss's law, which is where we landed at the end of last class, Gauss's law in the middle of this page says, in mathematical terms, it says, I mean, if you remember that a circle, okay, so let me back up. Remember, it's Gauss's law, the left side of Gauss's law, it refers to the flux, the total amount of electric field through some area, double integral means area. But you notice that there's a circle around that double integral. Remember from the beginning of this semester, we had integrals of dot products called path integrals. Our integrals were the continuous sum of a bunch of products that we calculated while walking along in our minds, walking along some path along, in effect, some x-axis of some function, right? But when we put a circle on the integral, we meant that the path was closed. A circle on an integral meant a closed path integral. It meant the continuous sum of products if you walked from some location all the way somewhere and then back to that original location. If you made a round trip, a closed path that we were talking about at the beginning of the semester, a closed path meant a path for which, if you kept on walking in the same direction always, you would eventually land where you started. Well, a closed surface is the same idea, extrapolated into 2 dimensions. A closed surface is a surface not like this. This would be an open surface. A closed surface is like the surface area of the Earth, or the surface area around on the outside of some cube, i.e. a box, right? A closed surface, what in English is often called a surface area. A closed surface is a surface that wraps around and touches itself, meets itself, so that anybody who would walk in the same direction forever along some closed surface would eventually end up back where they started. Gauss's law says that if you compute the net electrostatic flux going out of any closed surface anywhere in space, if you imagine a container of any size or shape anywhere in space, the total amount of flux emanating through that container is fully determined by the total magnitude of charge enclosed within that container. The flux through a closed surface is fully determined by the charge enclosed within that surface. Right. Now, the way we derive what we did last class is we focused our attention on the very simple, comparatively simple case of one point of charge causing field lines, and we imagined the sphere, a perfect sphere around that point, centered at that point, and we asked ourselves, what is the flux coming out of that? What's the electrostatic flux coming out of the surface area of that sphere? And what we realized on Monday, oh, you know what? Flux is field times area. And we realized if we looked at the area, the surface area, wrapping around some sphere centered on some charge, we realized that no matter how big the sphere was, big or small, we would get the same amount of flux either way, because we realized that, all right, flux is field times area. And if you picture a sphere surrounding a point, if you picture a sphere of bigger and bigger area, you would think that, I would think that we would get more and more flux because we have more and more area. But as a sphere grows, the area of the surface area of the sphere grows proportionally to 4 pi r squared. And the thing is that as that area gets bigger and bigger proportional to r squared, the strength of the field at any given place on the sphere weakens directly proportionally to r squared. The surface grows as r squared, but the field strength weakens as a function of r squared. In other words, the field lines spread out. They get less and less dense by a factor of r squared, or 1 over r squared. So we realized, okay, if you double the radius of some sphere, you're going to get 4 times as much surface area, but at every bit of the surface area, you're going to get 1/4 the field strength. So you get the same flux coming out of a sphere from a point, no matter what the size of the sphere is. Gauss comes along and says, you know what? That was a nice, handy, sort of vivid example that we all did with a sphere surrounding a point. But Gauss says, you know what? It's easier to see that truth with a sphere surrounding a point, but it's actually true no matter what shape you pick. Gauss says, look, if you realize that the sphere can be bigger or smaller, and it doesn't matter what the radius, what the r of the sphere is, you're still going to get the same flux either way. Gauss says, well, then in your mind, think of that sphere as being made of clay in your mind, start manipulating the clay and warping that sphere into some other shape. Like pop out some part of the sphere over here, pop out another part over here, warp it and deform it. Pardon me for saying, yes, I'm teaching. Yes. Today's Wednesday, so it goes for a while. Pardon me. Sorry. It goes till 7:04. Yes. And today, okay. Have a great time on the horse. Love you. Okay. Love you. Okay. So if you think about it, changing the sphere to some other shape, like a cube, means poking and prodding the size of R throughout that sphere. I mean, bye, love you. Love you. Love you. What is a sphere? A sphere is the locus of points equidistant from a given point. The whole thing that makes a sphere is that R is the same everywhere along the surface of the sphere. If you start, oh, wow, sorry, there's a question in direct chat. Great question. Okay, I'm going to pause for a sidebar for a second. I mean, there's a great question in the direct chat that says, if the shape is open, if I don't put a circle on that integral, do I always get an answer of 0? It's a great question on 1,000 levels. I'm not going to spend too much time on it because I don't have the time, but I would just say quickly, it's a great question, but the answer is no. The equation doesn't necessarily have to equal 0, but the key is that it doesn't equal a constant. The equation will equal different things for different situations if it's not a closed surface. If it's a closed surface, the total flux will always be fully determined by the charge contained within the closed surface. And this is what I'm trying to explain right now. In other words, we're not saying that if the shape is open, we get 0. We're just saying we can't have a fixed prediction. It's not always the same answer if it's open, but we do know that if it's closed, it's always the same answer. And here's why, or here's what I'm getting at. Even if you change that closed shape from a sphere to some other shape, like a square, what you're really doing, if you think about it, is you're making R not constant. If you make a square, or if you make some wacko shape like I have here on the picture, some oblong rectangular prism that's off on an angle, it looks all asymmetric. It looks all like who knows what's going on. But the thing about that shape that makes it not a sphere is that R, the distance from the edge of the shape to the center, is different at every point on the shape. So it looks like a jumble. It doesn't look like a perfect sphere. But what we just proved yesterday, 2 days ago, is that the R's cancel out. The result is independent of R. So it doesn't matter if the R is changing from one corner of the shape to another. R doesn't determine the flux through the container. So what I'm trying to say right now is 2 days ago, we showed that given the shape called a sphere, it doesn't matter what size it is. Now I'm saying, if you really think about it, if it doesn't matter what size the sphere is, then it doesn't even really matter whether it's a sphere or not. The total flux coming out of a container will be fully determined by the amount of charge within the container. And even if there's a point over here or a point over here and a point over here, or a whole bunch of points of charge, each one of them will produce this effect. So the total effect is true for all of the points of charge. In other words, at the end of the day, and you might want to write this down, what we're really saying is the electrostatic flux emanating out through the surface of any container is always fully determined by the total magnitude of charge within the container. Okay, that's what's already written here. And what that really means is the net electrostatic flux is independent of, so here's the thing to write down. The flux does not depend on size of container, size of closed surface, that is, size of container, shape of container, shape of enclosed charge, or amount of any charge outside that container. Like we're getting a result here that's we're saying the total flux out of a container is fully just determined by how many charge points there are inside the container. Any charge points outside the container don't matter at all because they'll create field lines that might enter in the container at one edge, but then they'll come out of the container at another edge because field lines go on forever. So one of the reasons we care about flux is it has this property of being really, really predictable, really, really constant, as long as we're looking at the flux coming out of any closed surface, as the direct chat person asked. Now, again, I know, I'm guessing, if you're like me at all, you're finding a lot of what I'm saying very abstract. Don't lose faith. If all what I'm saying seems very like, even if you're like, I sort of get what he's saying, but I don't really understand what it has to do with anything, or like why I would care, or like what does this physically mean, what he's talking about. Let me back up and remind you. That, and please write this down. I don't have it written down here, but we've written it before. Remember, flux means field strength times area. Flux is field strength times area. Again, you might still be thinking, I don't know why I care about that. Why do I care about field strength times area? Here's another reason. Here's a reason I'm going to give you right now. I've said it once before. We care about flux, field strength times area, because when we're drawing or picturing field lines, remember that field strength is represented by number of field lines per unit area, right? Field strength means density of lines. So and that's why we say here, like the field is getting weaker and weaker as the lines are getting more and more spread out, right? So if flux is field strength times area, and if field strength is number of field lines per area, and that is what I'm saying, right? So I'll say it again, and please write it down. Flux is field strength times area. But field strength is number of field lines per area. So flux is number of field lines per area times area. The areas cancel. Flux, in the end of the day, after all of this stuff that I'm talking, all of this mathematical abstraction, these integrals and these dot products and everything, at the end of the day, when we talk about the flux through a closed surface, we're really actually just talking about the number of lines, the number of field lines that go through a surface. And please remember that even though these lines are just a representation, and even though the lines that I draw on a page are just some number, even though lines are actually everywhere in space, and the ones I draw on a page are just a sampling of those lines, remember that we always use a consistent scaling factor when we draw a field line picture. So if we have 8 lines, so if I see 8 lines coming out of that one positive unit of source charge, that plus Q, if I have 8 lines that are coming out of that Q, that means something. That means a certain amount of charge, a certain amount of field strength, a certain amount of newtons per coulomb is coming out of the Q right in the inner neighborhood near the Q. What Gauss's law is really saying in the end is, hey, surround that Q with any kind of shape you want. It doesn't matter if it's a sphere or a box or a pyramid or whatever. If 8 lines are coming out of the Q, then 8 lines are going to bust through the container, no matter what the container looks like, right? Please follow this. If you were losing me before, I'm now saying something that hopefully you'll regard as so simple and straightforward. Again, you'll be like, oh, is that all he's saying? I don't even know why that matters. I am saying flux just means number of lines. If we say what's the total flux hitting the inner surface of a sphere, we really just mean what's the total number of lines hitting the sphere. When I utter this Gauss's law and say the flux through a closed sphere is always fully determined by the charge, I'm sorry, when I say the flux through a closed surface is fully determined by the charge enclosed, contained within that surface, I'm really just saying that if 8 lines come out of a point of charge, then 8 lines have to go out of the container surrounding that charge. What I'm saying is really, really self-evident. If instead of picturing if instead of picturing charge and field, you picture like a sprinkler on a yard, on a lawn somewhere in Long Island or something, picture a sprinkler with water coming out of it in all directions, right? And now picture that you make a tent. You build a tent around that sprinkler, or you put a sprinkler in a tent. So you've got some tent of some bizarro shape surrounding the sprinkler, and water's now hitting the inside of the tent, and you let the water sprinkle for like an hour or whatever, and you count up all the water drops that collected on the inside of the tent after an hour, right? You measure all the moisture on the inside of the tent after an hour, and you get like, I don't know, 40 gallons, whatever you get. Doesn't it make sense that no matter what the size is of that tent, or no matter what the shape is of that tent, the total amount of water you get on the inside of the tent is always going to be the same total amount? It's going to be just whatever amount of water came out of the sprinkler, right? Like with water, it's completely obvious. I should never say that, but I think it's fairly straightforward to say that with water, the total amount of water collected on the inside of a container is independent of the size of the container, independent of the shape of the container, independent of any water that's coming from the outside, because if it comes in from the outside, it'll go through, whatever. And it's independent of how the sprinklers inside the container are arranged. The total amount of water that hits the inside of a tent is fully determined by the total amount of water that came out of the sprinkler, right? Like duh, I think. If you're thinking that what I'm saying now seems clear enough that you don't even know, like, so what is the big deal then, Yaverbaum? Why are you screaming about this for 2 days? Here's why. What I am saying, what Gauss is saying, and I will go on in a minute, but the big point I'm trying to emphasize here toward the end of the course is a big point. I'm saying, Gauss is saying, field lines act just like water. Field lines are neither created nor destroyed in empty space. Field lines only start because of positive source charges that start them, and they'll only end if they hit a negative source charge, sink charge, that catches them. Other than that, field lines don't start or stop in space. So any number of field lines that you start with at a charge have to bust out of any container enclosing that charge. What we're saying is just field lines act like water. Field lines act like water. But now stop and realize what that means. We're saying field lines act like water. Water's a thingy thing. Of course, it's made of particles. Of course, particles don't just materialize out of nowhere or disappear out of nowhere. If you start with a particle, you end with a particle. What we're now saying, but field lines are not particles. Field lines are the information describing particles. A field line, when we say there's a field line over here, we're not actually saying there's a thing over here. We're saying there is a package of information describing a thing over there, right? That's what field lines are. Field lines are unthingy. They are not material. They are not particular. They are raw information. That's what field lines are. What we are now claiming when we claim Gauss's law, we're claiming that these field lines, which are just raw information, act like lines of water. Like what we're saying is, you can really take these field lines really seriously as representations of these fields, of these bits of information. You can take these field lines so seriously that in your mind, you can regard them as like jet streams of water, which means what we're saying is unthingy things, raw information in the universe sits around and behaves and exists as really and as actually as objects do. If an object exists, it produces the information describing its existence. It plops its vital statistics into space, and those vital statistics do not ever spontaneously disappear or decay or shrink or go away. The vital statistics, the information remains in space and can be moved around in space or not moved around in the same manner as droplets of water remain in space. That's what we're saying. We're saying the unthingy things, the unthingy raw information known as field lines are conserved. They're not created nor destroyed spontaneously in space. Unthingy things known as information act like thingy things. That's part of the number of field lines is conserved in the manner of actual particular matter. That's what we're saying. Okay, now I'm going to go on. I just try to just like, remember the whole course is about thingy things and unthingy things. So now we're saying unthingy things can really be treated as thingy things. That's like what we're saying. Raw information is conserved. That's what we're saying. Now, when we go on and remind you about this raw information, remember, I keep saying that field lines over here indicate or impart or transmit the information describing stuff, i.e. charges or masses over here. But remember again that what I was yelling about 2 days ago, that the way field lines do this is they communicate information through asymmetry. The field line pattern is only as asymmetric as the shape of that which caused the field line pattern, right? So again, remember, if you have a dot or a sphere or anything, if you have a point of charge, that's zero dimensional, right? I would regard a point of charge as having zero dimensional asymmetry. That means it's asymmetric in no dimensions. A dot, there's no dimension of space that is treated differently from any other dimension of space by a dot, right? And the field lines reflect that. A dot, a point of charge, sends out field lines symmetrically, equally along every axis of space. There's not one axis of space that's sort of preferred or labeled or treated specially by a point of charge. So a point of charge has a zero-dimensional asymmetry. It creates a field line pattern that has zero-dimensional asymmetry. But now, if you were to imagine a line of charge, like a point of charge, point of charge, point of charge, point of charge, all next to each other, like a big row of electrons, like in a wire, like in the lab. Now, I'm just talking about electrons just sitting there, right? Or protons just sitting there in a wire in a lab. Well, each one of those points of charge would create field lines that radiate out in all directions, right? But a proton here would create radial field lines next to a proton here, which would create radial field lines. And this, so one field line that goes up and to the right from this guy, as we've seen now a number of times in different examples over the week, a proton that creates a field line going up and to the right would be next to a proton that creates a field line going up and to the left. So we've got these two field lines like this. Remember, we said field lines never cross. Like the leftward component of one would cancel out with the rightward component of the other. Like we're doing vector sums here, like you did a week ago. And you'd just be left with field lines pointing up, right? In other words, a line of charge, if I put a line of static charge right here in the lab in front of you, it would create field lines that would radiate out in all directions like spokes. It would create radial lines that go out in all directions like spokes in all directions except for the direction of the line itself, right? Like if I put like a caterpillar with its legs, right? If I put a line of charge here, it's like a bunch of points. They'll all radiate out in all directions. So not parallel lines, radial lines, but in all directions except for that dimension that the charge is along, right? So I would say that's an example of one-dimensional asymmetry. We have symmetry in all the axes except for the one that the charge is along. That axis would not get any spokes. So that field line picture tells the universe, like if you're over here in space and you see these spokes coming out in all directions except for one, all dimensions except for the x-axis, space would be like, oh, there must be a bunch of charge along the x-axis. If the field lines are treating one axis as special, it means the charge causing the field lines is treating one axis as special. Similarly, if you make a plate of charge, you've knocked out two dimensions. You have charge along the x-axis and charge along the y-axis, let's say. Then you'd have field lines only going out along the z-axis. Again, I'm just trying to reemphasize that the field line picture shows space what's going on by virtue of how asymmetric it is. If there's asymmetry along, if there's only field lines along this axis, if there's field lines missing along this one and this one, that means there's charge along this one and this one, right? So again, field lines are as simple and as symmetric and as smooth as they can possibly be, given how simple or symmetric or smooth the thing that causes them is, right? Field lines are always the simplest possible picture or pattern to convey whatever complexity is causing them in the first place. Why do I say all of this with 16 minutes left? Because what if we now go one level higher in complexity? What if we have a line of charge that's moving all the time? A line of charge that's continuously flowing in one direction, like a current, capital I, right? What if we now look at a bunch of, like a row of charge that's constantly marching forward in front of us, on and on, because it's part of a wire that's attached to a battery, like you did in the lab. You know, we're standing in the middle of some big closed circuit, and we see this steady flow of charge always going past us. Now think about that for a minute. That is one step more complicated than charge just sitting there. Just like velocity is one step more complicated than steady position, right? If you see charge flowing past you, that's a different situation from charge sitting in front of you. But if charge is flowing past you continuously at a steady rate called a current, right? If there's always 5 coulombs passing by a single point every second, then then all these charges, each one of these charges is creating field lines that are radiating out in all directions, but each charge is sort of carrying its radiating field lines with it. So you got radiating field lines radiating, but they're all moving all the time. They're all flowing. So there's no way it's the same picture as that caterpillar spoke picture. It's some other picture that's slightly more complicated, but it's got to be itself some kind of steady, simple, symmetric picture. There's got to be, like when the lines keep moving and moving, they've got to eventually be canceling themselves out and falling into some steady pattern, just like when you were in lab 3 and you shook the string. You know, you're standing on 2 opposite ends of a long string, and you're going like this over and over and over again, so that there's all these crests and troughs going back and forth over and over again in the string. Eventually, since even though they're all moving, they're moving in a steady velocity and a steady pattern. Eventually, they all interfere with each other. Sorry. Eventually, all the crests and troughs fall into a pattern of patterns with themselves, and what started off like this ends up just being like that, right? Same thing here. If a bunch of charges are flowing continuously and constantly, we're going to get a pattern that's different from just the field lines that we get if the charges are sitting still. But we should still get some sort of pattern. In fact, we should get some sort of steady pattern if the flow is steady. We should get the simplest possible pattern of field lines that we can imagine for flow. And we do. Now, it turns out if you put steady flow near another steady flow, the physicist named Oersted in the 1800s, along with other physicists named Ampere and Biot and Savart, a bunch of physicists in the 19th century, once they sort of discovered, they were playing with voltaic cells and wires and resistors, and they were sort of discovering all this electricity stuff that you discovered in the lab recently. And they played with the idea of putting one steady flow next to another. It turns out, one current next to another. Turns out, if you put a current near another current, sure enough, action at a distance occurs, and it turns out that the two currents attract toward each other, which is very interesting. Now, it certainly has a lot to do with the fact that there's charges in there, but it seems also to do with the fact that there's now charges in motion. In fact, if you put the two wires next to each other, there sure are a bunch of protons in one wire that sure are attracting all the electrons in the other wire, but the protons in the first wire are also repelling the equal number of protons in the other wire. So nothing happens when they're just sitting there. And if you say, well, what if you put in extra protons in one of the wires and extra protons in the other? Yeah, if you put extra protons in one wire and extra protons in the other, then there will be interaction, but they'll repel each other. It turns out if you send the protons, really the electrons, in motion in one wire and you send them in motion in the other, you get this attraction. It's It's a different effect from just electrostatic attraction or repulsion. Flow attracts other flow through a distance. Whenever we see interaction through a distance, we attribute it to a field. Now, this field isn't strictly simply an electrostatic field, because when the charges are just sitting there statically, they don't do this. Once they're moving, they seem to do this. So there's some field that is pulling the two wires together that's due to the moving charges. We call that field the magnetic field. We designate it with a capital B. I don't know why it's a capital B, but it is. So this field that's clearly somehow related to the electric field, that seems to have to do with the electric field being in motion, is its own thing in a way, and we call it, or it's some other component or something, we call it the magnetic field. We designate it with a B. And if we believe it's a field, then it can be designated with field lines in as simple as possible way as possible, given the situation. So the question is, what do these field lines look like? What do magnetic field lines from? Okay, so I just said something this is very important. I'm saying it kind of fast. I'm saying just as static charges sitting around create electrostatic fields, charges in motion, or put another way, electrostatic fields in motion create a field line pattern that is new and different, but still a field. This motion field is called the magnetic field. Ultimately, what magnets are a result of this whole situation. So magnetic fields are caused by charges in motion. If electrostatic fields are caused by point charges sitting around, magnetic fields are caused by currents. And in the simplest possible case of a long straight current, the question is, what will the magnetic field lines, what will the field line picture of this due to this flow of charges look like? Well, remember, remember the pattern of field lines has to be as simple and as smooth and as symmetric as it can be, and while still conveying whatever asymmetry or complexity is causing it. So we need some sort of picture of lines that would convey the fact that there is a line of charges marching, flowing in some particular direction. If you really think about it, and you may want to think about this for a while, the picture cannot be spokes going out of, it can't be that the field lines spoke out of this current. The spoking field lines are what is produced by a static line of charge. If a bunch of protons are just sitting around in a line, they create field lines spoking out in all directions. But if the charges are now moving, all those spokes start moving and they start interacting with themselves, they definitely form a different picture. And they've got to form a picture that shows space, not only that there's a line of charge there, but that the line has a particular direction. It's going one way or the other. Well, the simplest possible picture of field lines that can result from a line of moving charge. Oh, well, okay. So sorry. So first of all, this action at a distance between charge flows, or this action at a distance that's created by the flow of charge by currents, is called the magnetic field. And the magnetic field is designated with a capital B for whatever reason. So I'm saying that again. And the most symmetric yet complete possible, or there goes my board, of course, right at the, hold on. Okay, the most symmetric yet complete picture, the most complete possible arrangement of field lines, which could be generated by a long straight flow of charge. Now, my drawing is very hideous here. You might want to look up on the web. You might want to type into Google Images magnetic field lines or B field lines from a long straight current. Like that's what I'm talking about here. What I'm saying is the field lines will loop around the current. If the current is going like this, like along the direction of my thumb, the magnetic field lines will be concentric circles wrapping around the line. Like at any given point in the line that you look, there'll be a circle going in a certain direction, and then a circle outside it, and then a circle farther and farther away. In other words, lines will get less and less dense as you get farther and farther away from this current. But these lines that are getting less and less dense, as they should, as you get farther and farther away from the current, are concentric circles everywhere you look on the line. So like a circle here, a circle here, a circle here, and then getting farther and farther out. And the circles have arrowheads on them, as field lines always do. They have direction. If the current is going like this, the field lines, if the current is going like in the direction of my thumb, the field lines will go like in the direction of my fingers. If I turn my thumb around, then the field lines turn around. This, again, it's a different picture from the other picture. The electric field is caused by a point. The point sends lines out symmetrically in all directions, sends out rays. This field is caused by a vector, by a current. The simplest possible set of line patterns that a current could generate is circles going around it. Like, it's a different picture, but it's equally simple. It's as simple as it could be given the thing that creates it. I'm going to say this one more time. A point of charge creates electric field that radiates symmetrically out from it in all directions. A vector of moving charge, right? So now I'm looking at a line with an arrow on it, right? A current, in other words, creates field lines that loop around it. Dots create lines, lines create loops. Each one is following the rule of field lines being the most symmetric, simple possible picture they can be for the situation that creates them. But we're talking about two different situations now. One situation is a dot of charge. It creates field lines that go like this. If you line up all the dots of charge in a line, then you'll get a bunch of spokes of electric field lines. Now you set those lines in motion. Those spokes will start crossing over themselves and moving along themselves and interacting, and they'll fall into a formation which is loops around the current line. These loops are called magnetic field lines. They're caused by moving charges. They're caused by electric field situation changing in a constant way. So I'm saying in sum so far, and I know we have 3 more minutes, but we're just about there. Magnetic field lines are caused by charge flow, i.e. by current. They're known as B field lines, and you notice they form closed paths. Electrical field lines are radial lines. Remember, they either start at a positive or they come in from infinity, and they end at a negative or they go off to infinity. Electric field lines are rays that emanate from a point. Electric field lines can only be caused by a point, so a point sends out these rays, and then the rays are neither created nor destroyed. If you have a bunch of points that are flowing in a line, in other words, if you have a charge arrow known as current, it creates loops around it. It creates not rays, but closed paths. Again, it's the simplest possible picture that you could imagine, given a source that is not a zero-dimensional point, but in fact a one-dimensional vector, right? Magnetic field. So electrostatic field lines are rays. Magnetic field lines are closed paths. They themselves, the magnetic field line, they have direction. They go this way or they go that way, but they close in on themselves automatically, always, because they're spiraling around some line, some axis with direction that caused them, right? What causes magnetism is a current, not a dot, a flow. Therefore, last page and last point. If you were to ever to go to any if you were to picture a container and say, can I do Gauss's law with magnetic field lines? Like, can I think about magnetic flux? Like what we were saying in the beginning of this class is if I draw any container or imagine any container in the universe, The total, I can count the total amount of lines fluxing out of it. The total number of lines going out of a container will be fully determined by whatever charge is within that container. Can I do the same kind of analysis with magnetic field lines? And the answer is yes, you could do the same kind of analysis, but here's where the direct chat person's question comes into play from earlier in the class. If you draw a container anywhere in space and ask how many magnetic field lines are fluxing out of this container, you will always get a net answer of 0, because any magnetic field line that might come out is necessarily eventually going to come back in, because magnetic field lines are closed paths. Electric field lines are raised, magnetic field lines are closed paths. Again, this all may sound very abstract. It is abstract, but I promise it's the last 2 pieces in a puzzle that we will finally put together on the very last class on Monday. Don't worry, I will tell you then how to prepare for the final exam. Don't stress it. Just listen carefully and follow the material and let it sink in. You've been very, very good. I'm already starting to miss you people, but we have one more class. I will put this together, the 2 facts, the electric field fact and the magnetic field fact, together in the last class on Monday. If you can't be there, please do get the notes from someone or get the video. Okay. I'm going to hang out for a second if there's any questions, but I have another class right after this. So have a nice day. Thank you. Have a great day.
Bye, Professor.
Bye.
Bye. Have a nice day.
Bye. See you. Yes. See you. Yes. Oh, have a nice day. I mean, yes. Okay. Yes. Thank you. Happy Mother's Day to you too. That's awesome. Thank you for reminding me. Good thing I ordered the gift. I think I got the, yes, thank you. Okay, should I, oh, I'm gonna stop the recording. Wait, I'm stopping the recording.